Ava Obenaus, apologies, from the University of Washington. She's a trainee of Dr. Nathan Snidiaki at the University of Washington. Thanks.
Hi, thank you so much for the introduction. My name is Ava Obenaus, and I'm a PhD student in mechanical engineering. I work with Professor Nate Snidiaki at the University of Washington. And my work that I'm going to be talking about today is motivated by infective endocarditis. This occurs when bacteria enters the bloodstream and then interacts and binds with platelets and forms these vegetations on the surface of damaged cardiac valves. And we are specifically interested in Streptococcus gordoni, which is a oral streptococci, which can be found in dental plaque. And Streptococcus gordoni has sick-like glycoproteins that are able to selectively bind to cilioglycans, which are on GP1B alpha. So I know we've talked a lot about VWF today, von Willebrand factor, and how it's necessary to initially adhere platelets to the site of injury. But what we haven't talked about so much is GP1B alpha, which is where VWF actually binds to platelets. And this leads to adherence and aggregation, but also there's a mechanosensory domain in GP1B alpha, which when it's tugged on under shear flow or some sort of tensile force, this can lead to downstream platelet activation. And so one of the questions that we're asking today is, what role does cilioglycan selectivity play in bacterial thrombus formation? And so to do this, we have 4 strains of streptococci that we are studying. The first one is M99, which binds specifically to core 1 cilioglycans, and this is our wild type strain. But then we also have a few other strains. So we have 10712, which binds specifically to core 2 cilioglycans on the mucin stalk of GP1B alpha. And then we also have HSA, which is able to bind to both the core 1 and the core 2 cilioglycans on GP1B alpha. And then as our negative control, we're using the strain R484E. While it is not able to bind to cilioglycans on GP1B alpha, it is still able to bind non-specifically to platelets through the Fc receptor. And so in order to study this question about cilioglycan selectivity and thrombus formation, we are using a novel microfluidic device that was developed in the Snidiaki lab. It is intended to model arterial flow. So essentially, what happens in vivo is as you encounter an area where there is an increased shear rate, this will allow VWF to unravel and stretch, bind platelets, and lead to thrombus formation. So in our device, we have these blocks which create this high shear gradient, and then that eventually leads to this thrombus that is able to form, and we can get certain measurements from that. And we'll talk about what the post is for in a few slides, so hang tight. So one of the things that we've looked at is aggregate area using phase videos. And it looks something like this in our device. So these are 8 discrete thrombi that are growing over the course of 3 minutes. And what we found is that with all 4 strains of bacteria, this increases aggregate area. But what's interesting is that our core 2 cilioglycans are increasing the area more than our core 1 cilioglycans. And you can see that in the difference between the 10712 and the GSPB strains, which bind to core 2 cilioglycans and core 1 cilioglycans, respectively. All right, so as promised, I was going to talk a little bit about the post in our device as well. So essentially, as we have blood flowing through our device and we form these clots, we first use a very high shear rate, 24,000 inverse seconds, to rapidly form these clots, and then we drop it down to 640 inverse seconds. And what this allows us to do is it allows the clot the ability to contract without being pulled on by these large drag forces. And so we can actually measure the contractile force of the clot, which is essentially like actin and myosin in the platelets sliding past each other, which we think shows shape change and can be a marker of platelet activation. We can measure the deflection of the post, and then using Hooke's law and a known spring constant of the post, we can use that to back calculate the contractile force. And so once again, what we see is the Streptococcus gordoni for all 4 conditions increases thrombus contractile force, with the HSA actually having the highest contractile force. The HSA is the streptococci that binds to both the core 1 and the core 2 cilioglycans. This is looking at bacterial incorporation into the plug. So you can see over time how the bacteria are able to adhere. And we can image this, and what we found is that streptococci that bind to core 2 cilioglycans on GP1B alpha increase bacteria incorporation. So we're seeing that even though the plugs are larger for all 4 conditions, the HSA bacteria and the 10712 strains are both causing, or are both leading to more bacteria actually incorporated into the plug. And so with that, this leads me to a few conclusions. One is that bacteria is able to increase platelet activation and aggregation, as I hopefully demonstrated here today, but also that Streptococci gordoni binding to core 2 cilioglycans on GP1B alpha leads to not only larger amounts of bacteria incorporation, but also appears to increase thrombosis. And so, of course, more investigation is needed to see how this affects virulence in vivo and also disease progression. I do have some additional data showing PAC1 binding, which basically shows platelet activation through how much activated integrin alpha 2b beta 3 there is. So if you'd like to see that data, please feel free to stop by my poster. And with that, I'd like to thank our collaborators, especially Jose Lopez and Jumei Chen, who are both in the room today. So thank you.
Hello? Yes. So I need a naive question. So is the GP1B alpha, is the sialoglycan the same everywhere, wherever it's expressed? Is it
yeah, that's a good question. So if I'm understanding what you're asking correctly, is there's the core 1 and the core 2 cilioglycans. There's only one core 1 cilioglycan, and that's located somewhere close to the mechanosensory domain around this area. Mm-hmm. And then there's also the core 2 cilioglycans, which are located on the mucin stalk. So they are in different locations. And that's part of our hypothesis for why we may be seeing these different levels of activation. If you have bacteria binding here, it may be able to pull more so on the GP1B alpha and lead to further downstream platelet activation versus if it's bound close to the mechanosensory domain.
And does it matter the source of the platelet, if it's coming from the lung or from the bone marrow?
Oh, that's a great question. We have not looked into that. We're just using human whole blood, so I don't know, further investigation would be needed there.
Okay, great. Thanks.